So let me give you another example. It's not a concrete example, but a very important one. Suppose H is my Hamiltonian operator. Hamiltonian operator. What is the Hamiltonian operator? It's a total energy operator. So H is given by the p squared operator divided by 2m plus the potential energy operator. So suppose that H has eigenvalues En corresponding to eigenvectors psi of n. Now, one technical assumption we have to make at this point is that we assume that the eigenvalues are non-degenerate. What does this mean? This means that for each En, there exists only, for each distinct, I should say, distinct En, there exists only one linearly independent psi n of x. Okay, linearly independent eigenfunction. Okay, this will not always be true. When it's not true, what you have to do is that you have to find some other observable distinct from H such that they commute, and you have to find their eigenfunctions which are simultaneous eigenfunctions. Anyway, that's a technical assumption that I'm not gonna, so I'm making the assumption for sake of simplicity. This is a more complicated thing that we will come to some other time when this is not the case. So we are assuming that these eigenvalues are non-degenerate, means that for each value of En, there is one and only one linearly independent eigenfunction psi n. Okay? So, in other words, H acting on psi n gives me En psi n, and there is only one psi n for a given value of En. If that is the case, then you can show quite easily that the inner product between these eigenstate is going to be orthogonal or orthonormal. If M and N are continuous indices, then the right-hand side would be a direct delta function. Okay. So the fact that we assume that the eigenfunctions of H will provide us with a complete set of bases means that any wave function can be expressed as a linear combination of, say, psi n of x. So if I have some wave function psi as a function of, at some given time, then we can always express this as some coefficient of linear combination. These are complex numbers times psi n of x. These are the energy eigenstates. Eigenstates, eigenfunctions, these are used interchangeably. So any wave function can be expressed in this way. Okay? So now, suppose my system is in the state psi, this state. And I decide to measure the energy, say H. Now, what possible results can I expect? Okay, what possible results can I expect? Can someone answer me this question? হ্যাঁ মেহজাদ বলো
I
বলো
was no, I was just contemplating. No, I really don't have anything in mind. I'm sorry.
Okay, what did we say earlier when we make an observation of a Hermitian operator? What are the possible uh, outcomes of that experiment? It has to be a real number, right? So let me give you a hint. It's a real number. Okay. Anyone else wants to?
And it has to be one of the eigenvalues, right?
Exactly. So the eigenvalues answer is that En, one of the Ens. Okay. Right. That is the En. Now, if this is the state, suppose I get the answer En. What would be the probability that our answer will be En? Well, according to quantum mechanics, that probability is given by the projection of this vector, of this function, along the psi m axis, and then its square. Okay, so the square of the projection of this function along this axis. So geometrically, this means that if I take the vector, if I take the function psi and project it along the em direction, which is the interpretation of the inner product, right? Then this is of course a complex number. So if I take the square, modulus square of this, this is the probability that if I measure the energy, that the result of that would be Em. Okay. So if this is true, then what does it imply? Let's see. So psi m, so this means that we have inside the modulus an integral. So let me just switch back and forth between 3 dimension and 1 dimension. So this is going to be psi m of x star, psi of x squared, modulus squared, right? But what is the second factor? The second factor, according to this assumption that we can express it in terms of the energy eigenstate, is nothing but a linear combination of the energy eigenstates, right? And then we can factor this out of the integral. If I factor this out of the integral, I get n, Cn, and the rest I have psi m psi n. But we assume that they are orthogonal to each other, which I haven't proved yet, but that means that Cn delta of m of n whole squared. So if I now do this sum, then Cn, this sum will be replaced by just Cn modulus squared. So that is going to be the probability that if I make an observation on the system which is in state psi and measure its energy, then the energy will be given by, the energy will be Em. That probability is simply the square of the coefficient in the linear combination of the state psi expressed in terms of the eigenstates, okay? All right?